Hey everyone, welcome back to Robotics. I hope you guys are doing well. Today we're going to have our 7th lecture on velocity and motion. To get us started, I want to show you this video of an underwater robot. And this robot is swimming around trying to explore some wreckage. The key concept I want to show you in this video is the way the robot converts the different motion of its joints into the overall motion of its rigid body. You can imagine the robot turning on different fans in order to swim forward or backwards. And so a key question is, how do I convert those different velocities into the overall motion of this system? Well, to understand that, I want to cover it from 2 different perspectives in today's lecture. First, we're going to think about how we convert angular velocities into rotation matrices. And second, we're going to talk about how we convert screws into transformation matrices. So we're kind of going full circle here because we've talked first about what is a rotation matrix, what is a transformation matrix. Next, we talked about angular velocity and screws. And now I'm showing you how you can go from these different velocities and find the corresponding rotation or transformation from those velocities. Okay, so how do we do that? And as you might have guessed, if I've got a velocity and I want to convert it back into something like a position or rotation, I'm going to use integration. And so the first question is, how do I integrate angular velocity to find the resulting rotation matrix? So let's get started. Let's say that I've got a rigid body that is rotating with some angular velocity omega s. Again, this angular velocity is a 3x1 vector, and it captures the angular velocity from our spatial frame. That's us sitting there watching this body spin in space, or this coordinate system spin in space. I want to understand what rotation matrix is going to capture this motion. I want to start off with this equation, which is part of the definition of what is angular velocity. On the right side, I've got the rotation matrix at time t. On the left side, I've got the time derivative of that rotation matrix. So that's going to be dr dt. This will be a 3x3 matrix. And then in the middle, I've got omega s bracket. So reminder, omega s is a 3x1 vector describing the angular velocity in the x, y, and z axes. We use the bracket 3 notation here because we want to convert this 3x1 vector into a 3x3 matrix. You can also think about this as omega s cross the rotation matrix r. Now this equation, when I first look at it, probably seems a bit odd, but what if I rewrote it as x dot equals ax? This looks kind of familiar, right? Maybe you saw this in something like a class on ordinary differential equations. This looks like a more familiar equation. We kind of know how to solve this. So it's going to turn out we can take the same principles and apply them to this equation, which is a matrix differential equation. And we can solve it to find the equation right here. So I can solve line 1 to get line 2. Here, R0 is going to be the rotation matrix at time 0. So you can think about that as the initial rotation matrix or the home rotation matrix. R of t is going to be the resulting rotation matrix after t units of time. And then what I have right here is a very interesting term. It's going to turn out that this right here is another rotation matrix and one that we build from our angular velocity. To make that point a little bit more clear, let's say that instead of thinking in terms of time, I think in terms of some rotation angle theta, whether that's degrees or radians, up to you, right? But let's say that I have this equation where I've got my rotation at theta, I can find rotation at theta dot. Well, I can use the exact same process to get the corresponding equation down here. Now again, R of 0, that's my home rotation matrix. R of theta, that's going to be the rotation matrix after I rotate by degrees or radians theta. And this right here is going to be a very interesting term that we want to explore. Right? So instead of thinking in terms of time for this differential equation, I'm now thinking in terms of a rotation angle theta, and I've got this term. Let's expand this term and explore what it means. So it turns out that this e to the bracket omega s theta is actually a valid rotation matrix. It's a rotation matrix that satisfies both rules that we need to have for a rotation matrix. And what it's really doing is it's describing a rigid body that's rotating around the axis omega s for theta units. And again, since theta could be degrees or radians, again, up to your definition, this is like the amount of the angle that we're rotating, and this is the axis that we're rotating around. So what we're really doing here is we're converting an axis, omega s, and an angle, theta, into the corresponding rotation matrix. Now for implementation, this is a matrix exponential, and so you'd want to use something like EXPM as the matrix exponential in MATLAB. Let me show you how to do that. So we'll go to the next slide, and here I'll show you how I did this in MATLAB. So I start off by writing sims theta real, and that's declaring that theta is a symbolic variable, and it's a real number. It's not a complex number, it's a real number. So theta is the number of radians I'm going to rotate. Then I declared what axis I want to rotate around. Again, totally up to you what axis you want to rotate around. Just has to be some three-dimensional vector that captures your axis of rotation. Here I'm rotating around the z-axis, the positive z-axis. I wrote 0, 0, 1. And now in my third line, I apply our equation, this equation right here, in order to convert this axis and angle into the corresponding rotation matrix. So I've got bracket 3 omega times theta, and I get out what you see down here. So this is my 3x3 rotation matrix. And actually, this equation should look a little familiar if you flip back to previous lectures. This is the equation we already talked about for pure rotation around the z-axis. So this is equivalent to r, z, comma, theta, pure rotation around the z-axis. And so we've kind of got that same answer, but now just a different way. We now understand how to go from an axis and an angle and build out a rotation matrix. Okay, so that's how we can convert angular velocities back into rotation matrices. We can use the same sort of logic in order to convert screws into their resulting motion. So let's say that we have a joint that's moving with some screw S. And I want to understand what transformation matrix captures the motion of this joint. So if I were to actuate this joint, what transformation matrix captures the motion resulting from the movement of that joint? I'll start off with the equation we were just discussing. Just instead of thinking about it in terms of rotation matrices, now I'm thinking about it in terms of transformation matrices. Here's T of theta, a transformation matrix with angle theta, or translation theta, whatever your units are here. And then here's T dot, the time derivative of that transformation matrix. And here I've got bracket of S. Now, previously I was using bracket 3. Now I'm going to be using bracket 6. And the reason why is because S is a 6x1 vector. It's a screw. And so I need to use bracket 6 to get the corresponding dimensions. This is going to build out a 4x4 matrix. So I'll have a 4x4 times a 4x4, giving me a 4x4 for the time derivative. If I solve this matrix differential equation, I get the line 2 that you see here, where I've got T of theta is equal to E, the matrix exponential, of bracket S theta times T of 0. This is my original transformation matrix, and this is the resulting transformation matrix after moving joint S by units theta. And again, I really want to focus in on this. This is the key concept that we're covering in today's lecture. Because what this is doing is this is actually forming a transformation matrix from moving screw S with theta units. So again, this right here is going to be a transformation matrix. It'll have a rotation matrix in the top left, a position vector on the top right, 0, 0, 0, 1 on the bottom. And it moves along screw S for theta units. To implement this in MATLAB, you're going to want to use the EXPM command for your exponential. Let's see what that looks like. Maybe it'll make it more concrete. So I'm going to again say I've got some angle theta, or maybe distance theta that I want to translate. And I'm going to start off with a prismatic joint. So I'll make the screw for a prismatic joint. As a reminder, for these prismatic joints, the top 3 elements of the screw are always 0 because I don't have any angular velocity. And the bottom 3 elements are a unit vector pointing in whatever direction I'm moving. Here I'm going to move along the x-axis. So I'm saying, hey, I've got a prismatic joint that's lined up with the x-axis. So that's what I'm defining here in line 2. And then in line 3, I'm implementing our equation to convert this screw into the corresponding transformation matrix. So I'm saying, hey, I'm moving along this screw axis by theta units. Tell me what the right transformation matrix is that captures that motion from the spatial frame. Here's the answer I get. You can double check that this is a valid transformation matrix. It's got the identity matrix here, and it's got a position vector, and it's got 0, 0, 0, 1 on the bottom. It makes sense to me that I've got identity for my rotation matrix because I'm not rotating, right? It's a prismatic joint. I'm just extending and retracting, so I shouldn't really see any rotation matrix. Then for the position vector, I've got theta units along the x-axis, 0 in y and 0 in z. Well, that makes sense because I define this as a prismatic joint that is lined up with the x-axis. So when I move it by theta units, I should be moving by theta units along the x-axis, making this transformation matrix. Cool. So the main takeaways. If you want to convert an angular velocity into a rotation matrix, you can do so with this expression right here. What it's doing in words is it's taking an axis that you want to rotate around, that's omega s, multiplying that by an angle, how much you want to rotate, and building the resulting rotation matrix. You can do the same process to convert a joint with screw S into its transformation matrix. That's what's shown right here. So I'm moving along screw S by theta units, and this is building the corresponding transformation matrix. So What I can do with these two concepts is I can convert motion, both direction and amount, into a corresponding rotation or transformation matrix. And importantly, this motion is defined in the fixed frame S. And you know that because I've got this lowercase s here to say, hey, this is the angular velocity from the spatial frame. And we know that these screws are always defined in our spatial frame. So again, I'm converting my direction of motion, whether that's omega s or just my screw s, and then the amount, theta, I'm converting these two elements into my overall rotation or transformation matrix. Cool. So today we've talked about how you can go from angular velocity into a rotation matrix, as well as from a screw into a transformation matrix. To reinforce your understanding of these concepts, I encourage you to go through the practice set. It's in the description or the pinned comments. The first page has got the questions, and the following pages have the answers to those questions. Once you've completed that, in our next lecture, we're going to start to think about what happens when I have multiple robot joints. Right now, we just talked about, well, how do I map one joint into a transformation matrix? But what if I have multiple joints? How do I build the overall kinematics of our robot arm? So I'll see you next time.